Okay, for the dreaded chi-square statistical analysis. This is not that hard, but people freak out about it. So let's just go through it. The chi-square is used to test how likely it is that an observed distribution is due to chance, right? In other words, do your observed results fit what you expected? So when you collect data, is the variation of your data due to chance, or is there something else there? For example, in genetics, we often ask, is the genetics what Mendelian expected, or did you get something funky, meaning there might be gene linkage? So when we look at the equation, this means the sum. O is the observed results. E are the expected results. And our goal is always to ask whether you are rejecting or accepting a null hypothesis. The null hypothesis states there is no significant difference between the observed and the expected frequencies. You can flip a coin 100 times. If you expect 50-50, right, at the end. However, maybe you get a result that's 62-38 or 49-51. And what you use a chi-square to do is say, okay, are these observed results what I expected, or is there something funky going on? Like, do I have a weighted coin? We always are going to use a table called a degrees of freedom chart to determine, to kind of use statistics to ask whether our observed results match our expected or not. So the degrees of freedom are always the number of outcomes that you're expecting minus 1, right? And I usually look at this probability at the 0.05. Here's my degree of freedom. If your number of your chi-square is above this, you're going to reject the null hypothesis. If it is below, you're going to accept the null hypothesis, right? So if your chi-square number is below, you accept. Above, you reject. This is kind of what is on the AP equations thing, which I will post for you, the AP biology equation sheet. I will post that so you guys have access to that during your cumulative exam. So let's do a quick example of this. So here we're looking at a dihybrid cross, meaning we're looking at two different traits. We're looking at body color and eyes. So here, black body eyeless flies cross to wild type. The F1 generation are all wild type, meaning that the wild type body color must be dominant and having eyes must be dominant. These are two recessive traits. The F1 cross when you cross the F1, which is what we expect, but we're now looking at the numbers of these, right? So to conduct the analysis, we always have to have a null hypothesis. In this case, the two traits are not linked and therefore segregate and assort independently. In other words, the differences between the expected and the observed are due to chance alone. So first, you need to determine what you expect the values are, right? What are the expected outcomes of a typical dihybrid cross, right? And you should be able to do a dihybrid cross and figure that out. If you're crossing two doubly heterozygous flies, then you expect a 9-3 to 3-1 ratio, right? The expected results, you need to know that ratio. So you need to say, okay, so to compute the expected, I'm going to use these ratios and multiply them by the total number. So I have this all written out for you. So for normalize, I'm going to take 9/16 times the total to get my expected, right? So now that we have our expected and our observed, we're going to use the chi-square formula to compute the chi-square for this cross, right? And you just use this equation. So we figure this out for all the different ones, and then we add them together. Here, how many degrees of freedom do we have? We had 4 phenotypic classes minus 1, 3 degrees of freedom. Here's our chi-square number, 0.2, and it is far lower. So that means that we are going to accept our null hypothesis, and the observed and expected are not different from one another. So that is kind of it. If you have other questions, there's lots of good online tutorials, or you're welcome to ask me as well.